class proper?
Yes, sir.
Give them to me.
On number 5 in the, what is that one called? Members lowered according to the rules of stress.
Oh, yeah. It's a catchy name.
So when we were doing this yesterday, we came up with 31 variables and 18 equations.
Oh, for the...
It's a big truss.
yeah.
So I looked at it and I well, we should be able to simplify this, but then I don't know how to retransfer the forces
Okay. So...
back into all these pins and beams and stuff.
mhm.
We also tried that one, and we took the moment from either endpoint, and we got different values for external loads.
Okay.
So we looked at an equilibrium, and like things are constantly changing. So
Okay, let's draw out the free body diagrams and count out the variables. And so it looks like this is number 5.
Yes, sir. Need a copy of that?
And yeah, sure, that'd be great.
We labeled things. What's that? Oh yeah, Louis, you want mine? How many hours do we have on that? You can get one. Many hours.
Okay, all of these are connected by pins. And you have a pin connecting connecting into the ground over here and a roller over here. And then a horizontal force of 400 and a vertical force here of 620. And I'll number them 1, 2, 3, 4, 5, 6, 7. So it should be 21 equations, 21 variables, doing it the way we did it in statics. So free body diagram of 1. We have, I'll call this A, B. So we have RA, and then we have the force on 1 by 2. Up here, the pin's part of member 1, so we have the 400, the force on 1 by 3, and the force on 1 by 4. That's member 1. Member 2, here we have negative force on 1 by 2. And then at the joint on the right side, the pin's part of member 2. So we have the force on 2 by 3, the force on 2 by 5, and the force on 2 by 6. Then a free body diagram for member 3. We have, the pin isn't part of this one, so all we have is the contact between 3 and the pin, so this is negative F13. Down here, same deal, so this is negative F23. Free body diagram of 4. Here we have negative.
You have F25 and F26
Because, in which one?
on free body diagram.
3, so why wouldn't we have 3, 5, and 3, 6?
Yeah.
Because if you think of that from the side, let me Okay, so if you think of that joint in the middle at the bottom from the side, you have member 2, member 3, member 5, and member 6 with a pin going through all of them. This is obviously not the way it would really look, but it's just sort of a way to understand how the forces work. We lump the pin in with the lowest numbered member. So that pin is part of member 2.
Mm-hmm.
So on member 2, we have contact with 3, 5, and 6. But on member 3, we only have contact with 2. This doesn't touch this or this. And same thing with the other one. So when you have more than 2 members meeting at a joint, only the lowest numbered member makes contact with more than one other one.
And that's the same with 3 on 4 then.
Yeah, right. So 3, yes, exactly.
That clears it up.
Okay, yeah, that side view thing actually is a helpful thing a lot of times if you get confused. It's easy to get confused on this stuff, and then just draw a little diagram of the
I
side.
remember you doing it last year.
Yeah.
But
Uh-huh.
Last
year.
night,
Yeah, that was a year ago.
we'll be able to solve it now.
Yes.
Is that only the case if there's no external force on it?
If there's an external force on it like that 400, then that's also, so the side view at the joint at the top where 1 and 3 and 4 meet, you have 1 and 3 and 4. And then you have this force acting on the pin. So this is 1, 3, and 4. This is the 400. And we treat the pin like it's part of member 1. So the 400 is applied to 1, but the 3 doesn't see the 400 and the 4 doesn't see the 400. The 3 only sees a contact with 1 and the 4 sees a contact with 1.
But the 3 wouldn't see contact with 4.
The 3 and the 4 don't touch each other, right? The 3 only touches 1 and the 4 only touches 1. Because this is all the shaded is a single thing. You know what I mean?
Yeah, makes sense.
So member 4, over on its right side, it's the lowest numbered member at that joint, so we have the 620. And then we have the force on 4 by 5, and the force on 4 by 7. And then free body diagram of 5. We just have up here, we just have the force on 5 by 4, so negative F45. Down at the other end, we just have the contact with 2. So negative F25. And then the 6 at the left end, it's touching 2. So that's negative F26. Over here, it's the lowest numbered member, which means makes contact with 7, and it also makes contact with that roller. So we have the force RB from the roller and the force on 6 by 7. And then 7 only feels 4 on the left, and it only feels 6 on the right. So negative F4, 7. Is that right? 4. Yeah. And down here, negative F6, 7. Okay, so what do we have? 2, 4, 6, 8. It's a little hard to keep track of all these. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 21. Hey!
And we'll get 21.
Yep, 21 equations, 21 variables.
We just gotta tweak what we did. We knew there was something we were missing.
Mm-hmm.
And we knew it was something simple, but we were thinking.
Oh, yeah, so you have all the extra ones that come from, like, the force on 3
We
by
did.
5 and
Yeah.
stuff like that. Okay, yep, that's the answer. Any other homework questions? Okay, let me have those back. I need these bigger, I guess. Yes?
Remember 7?
Okay, on that same set?
Yep, on that same set.
Yes. Yep, you can just use the truss method. In that case, you would have what? 1, 2, 3, and then, well, you'd have, I guess, 7. I think that's a system of 7 equations and 7 variables because you just need to solve for those. And then maybe you might have to do the, you might have to isolate the whole thing first, so maybe it's 10 and 10 or something. Yeah, but yes, you can do it as a truss.
So we can like do the external loads first and then do internal loads?
Yeah, you can do the external loads first, like do the reaction at A and the reaction at B, and then from there solve for the tension compression in each one of those.
Is there any way that you can do that quick? Because when we did
Oh, yeah.
we got different numbers
Yes.
for depending on where we took the moment.
Okay.
Um,
So first isolate this. And this was the one that you got different things depending on where you chose the about point?
yeah, so we did the moment about A, we got different values for AX and AY. And then if we did the moment about B, we got different values for RB and RAX and RY.
Okay. So Newton's second law says RA plus 400, 0, plus 0, negative 620, plus 0 RB is 0. If you do the moment equation about A, you get, how long is each of these members?
The,
They're all different.
no,
The bottom is 5 meter, the A to B,
Yeah, what's A to B?
that's 5 meter.
5 feet above.
It's what?
5
Like-
meter, whole thing, and
The
then
whole
A to
thing
B.
is 5 meters, so it's the 45 feet.
Okay, so 2.5, and then up it's,
Point 4555.
0.455
As the height.
okay,
The length of those is, what's that length?
okay.
0.3 something.
So, yeah, so 0.455 up. So you have negative 0.455 times 400. And then minus, that's 620 as a moment arm of 2.5, 3.75. Times 620. And then the RB has a moment arm of 5. So what do you get for RB from that one?
I think it's 469.
Okay, so now let's do it with the about point at B. So you have negative 5RAY minus 0.455 times 400. And then this one is plus 1.25 times 620. And so what do you get here for RAY? What? 191.44. And that 0.4, sorry. And that's positive? Okay. And so then if you plug that in here, yeah, those two have to add up to 620. So that gives you the same thing.
No. That's not correct.
They don't? Oh. Well.
But it's still not the same number.
My answer is not.
I have a different number for the height. Yeah.
Yeah.
1, 2, 3, 3.
You- 133?
That's the length of the arms.
Oh, the length.
That's the length of from RA to the 400.
So that whole,
The whole system is not in equilibrium, correct?
the whole system is what?
Not in equilibrium.
It is.
No, but my answer is not. Why don't we take the moment at different points than the band?
It needs to be the same. Okay, so if that height is, okay, so the height is, so this is the triangle. That's 20 degrees. This is 2.5. And so,
1.25, right? 1.25.
oh, 1.25, yep. Yep, 1.25. And so, 0.940 is equal to 1.25 over, so this length is 1.25 divided by 0.940, what's that equal to?
1.32979, so 1.33.
1.33. And then this one is 1.33 times sine of 20. So 1.33 times 0.342. Oh, 0.4.
0.455.
Okay, so that's what we used, right?
Yep.
And okay, so we got 400 times this. What?
The answer I gave is not right.
Oh, it isn't? What is it?
It's not right.
Everybody do it again.
Yes. This one minus 118.
This one?
Negative 501.4. Negative 501.4 is RB.
Yeah, that was
RB is pulling down.
Yep.
I got positive. Because you would add those two negative values, don't you?
Yeah, right. It has to be positive.
Negative 0.455 times 400 minus negative 0.37 or minus 3.75 times 620 is a negative number.
But then you move it to the other side.
and then the other side.
Oh, yeah, I stand corrected.
We had that equation, yeah,
But-
we did the math.
501.4.
501. 501. And then this one, does this one come out right?
I have 118.6.
118. 118.6. And then this equation says that those are correct within 0.4 newtons of each other, right? Because if you used one of these to solve for the other one using Newton's second law.
Yeah, I think we got that first one wrong, so.
Okay,
Yeah, no, I got it, thank you.
sure. And then once you have that, then you can just
Yep.
isolate enough pins that you have all of those forces represented. So you'd have like free body diagram of, so let me, so I call that A and that B. Let's call this C, D, E. So then a free body diagram of D would look like this. F1, F3, and F4. And you just have to do enough of these that you have all of those variables represented. Sure. Okay, Sophia, you had a question?
Is what number 7? How to treat the masses?
Mm-hmm.
Oh no, never mind. What's number 8? But number 7, I was confused because we did area of a triangle and then area of a rectangle. Number 7.
On that same set?
Yeah, you did the same kind of number 8 though.
Okay, so number 7, we have that, and it's not. So it's a different set. Is that
Yeah,
right?
that's a different problem set.
Okay. Okay. It's on the,
Internal loads.
okay. Do you have that one? Okay, so it's a cantilever beam on this side. That's the good side. And then a triangular load like this. (15,000 newtons per meter), and a torque at the middle of 1,500. Okay, this is a pain in the butt, because when we do a cut representing, so when we do the cut where the right end of our isolated piece is inside that distributed load, we're going to be, so we'll isolate something like that, and the distributed load that we'll be dealing with isn't going to be triangular anymore. You know, it's going to be a trapezoid, which you can think of as a triangle sitting on top of a rectangle. So let me go through that one. We don't have to do the thing at the right, because we'll never get to that for the internal loads. So there are two places. No, that's not right. N is equal to 3. The two endpoints, and then the distributed load changes at the middle, and that's the same place that we have a point torque. So N equals 3. We're going to have to do 2 cuts. And the first cut is the unpleasant one. The first cut is the deepest. Cut 1 is for x values between 0 and 0.45. And so we're going to isolate a piece like that, and we're going to be ignoring all this. And so we have to deal with this unpleasant reality. And then T, V, M, and torque. All right, so let's think about this trapezoid. I'm going to break it up into a triangle sitting on top of a rectangle. This side over here, the height is represented by the function for that line. So the equation for that line, you know, this is our q of x. That triangular load drops a total of 15,000 over a distance of 0.45, and it has a y-intercept of 15,000. When x is equal to 0, it has a value of 15,000. So what's negative 15,000 divided by 0.45? Okay, so negative 33,333.3 repeating x plus 15,000. That's the equation for this line. And when at the right end you're at the location x, that's the height of the graph. Okay, so that's the height of this rectangle. Over here, the total height is 15,000, which means that the height of the triangle is 15,000 minus this stuff. The width is x. So now I'm going to separate it out into a triangle and a rectangle. We can treat that as two different distributed loads. They both have widths of x. This one has a height of 15,000 minus 33,333x. This one has a height that you get from doing this subtraction, and you just end up with positive 33,333x. So the area of that triangle is 33,333x times x divided by 2. And the centroid is x over 3. The area of the rectangle is this times this, so 15,000x minus 33,333x squared. And the centroid is x over 2. So now that we've chosen the body to isolate, we can use these to represent the distributed load as point forces. So at the midpoint, we have a downward force of 15,000x minus 33,333x squared. And then a third of the way along it, we have a downward force of 16,666x squared. And then we have the internal loads. And these distances, this one is x over 2. This one is x over 3. And so Newton's second law says what we have is a magnitude of 15,000x minus 333x squared pointing in the negative y direction. So as a vector, that's 0, negative of this. So 33333x squared minus 15,000x plus 0, negative 16666.6 repeating x squared plus t negative v is equal to zeros. And then for the moment equation about the z-axis, well, you can solve for these. So there's no tension. The shear force is 16666.6 repeating x squared minus 15,000x. then the moment equation about the z-axis. The 16,000 x squared has a moment arm of x over 3. And if the about point's here, that's a clockwise rotation. So what's 16,666 divided by 3? That's probably all 5s. Is that right? Divided by 3. Okay, so you have negative 5.5 repeating x, and this is now x cubed. Then you have this one with a moment arm of x over 2. So that's 7,500 x squared plus 16666 x cubed. Then plus m minus vx equals 0. So m is equal to negative 11111.1 repeating x cubed plus 7,500 x squared plus vx and so you get positive 5.5 repeating x cubed minus 7,500 x squared for v. For that cut, the torque is equal to 0. Okay, so this one, we can check that. dm dx is equal to 16,666 x squared minus 15,000 x, so that makes sense.
Okay, yeah, my main question was on the versions, but I think I got the second part.
Okay. Yeah, the second cut is not too bad because once the right end gets past the distributed load, then it's just a number again. You don't have to represent that distributed load in terms of functions of x anymore.
So you just do it the first time around.
So when you do the second one, so now this is between 0.45 and 0.9. The whole distributed load is over here. And so now you can just represent this with a point force. That triangle has a height of 15,000, a width of 0.45. So the area, I guess 7,500 times 0.45. 3375. And the location is a third of 0.45, so 0.15. And so you can redraw that free body diagram with just a number, 3375, acting down. .15 meters from the end. This point torque here. And then you don't have any of the messy algebra in that cut. Yep.
So, just to reiterate, so the first cut is going to involve like the equation, looking for like, instead of a point four, so like
Mhm.
that, because we're treating it as a trapezoid, so you have to find the two areas.
Yeah, right.
And then because it's arbitrary, we use x, right? Like the location.
Well, our x always represents the right end of our cut. But wherever our, how big that the size of that trapezoid depends on what x is. So, yeah, whenever you take a cut that's inside a distributed load, everything's going to be represented as a function of x. It just gets messy, and this is especially messy because of the shape of the function. Any other questions about that one? Any other homework questions? For the test tomorrow, I just want to make it up through internal loads. So if you want to do more problems like this today, we can. Yep.
I was recommending number 8.
The next one?
Yeah, the next one.
Okay.
We had a mass, and I forgot how to.
Yeah.
Distributed load.
Okay. So the next one you have this point torque, and then the mass is equal to 500 kilograms. So the first thing is calculate the external loads. So you have a force vector here, a point torque here, an upward force, I'll call that RB. And then at the center we have the weight, 500 times 9.81, so 4905. And this is just going to tell us that the only joint in this problem that can counteract that 4,000 Newton torque is over here at the pin. So I'll call this TA, fancy TA. I wish I had a fancy TA. I could get your homework back. And so this will tell you that RA is equal to 0, 24, 24, 2, 4, 5, 2.5. And RB is equal to 2452.5. And then TA is equal to negative 4,000. Okay, so now for the cuts. N is equal to 3, so we're going to have to make 2 cuts. Yeah. You have the 2 endpoints, and then the only other things going on are at that midpoint.
Oh, yeah. Okay, so if more than one thing acting at the same point, you just want the internal.
Yeah, all you care about is the point. You don't care about the, like, is that point represented or not? That's all you care about. Okay, so cut 1 for x values between 0 and 3. Okay, so finally we got to your question. So how do we represent this distributed load? Well, we have the upward force of 2452.5. We have the torque this way of 4,000. The distributed load, so the weight, the total value of the weight is 4905 acting down, but that's distributed over a distance of 6 meters. That beam is 6 meters long. And so you just take the 4905 divided by 6, and that's the distributed load. So 4905 divided by 6 equals 817, and that's newtons per meter. And then you have the internal loads. And now that you've done that, you can represent the distributed load as a point force. And
on the forces on the left side, that's RA, is it not? Oh, wait.
Yep, RAY, yep.
There we go. Yep.
So you do R2L,
Mhm.
multiply 817.5.
No, you're missing one step. So, and actually drawing out that distributed load will help you not miss that step. So remember that you need to go from this to a point force. And to go from this to a point force, you have a rectangle with a height of 817.5 and a width of x. And so the area of that is 817.5x. The centroid is x over 2. And so you want to draw one more free body diagram before you go to your calculations. So you have a torque of 4,000, an upward force of 2452.5, a downward force at the midpoint of 817.5x, and then the internal loads. And now, when you go to the moment equation, you're going to multiply 817.5x times x over 2 negative to get that moment. Any other questions?
Anytime you have a math represented, it's automatically one more cut, and you can do that on the midpoint.
No, actually, that's an easy mistake to make, so be careful about that. When you have a mass, that's a uniform distributed load, so that distributed load doesn't change over the whole length of the beam. And so the weight never adds another cut. It's easy to think that it's going to, because when you treat that weight as a point force, it acts at the middle. But the point force that you use to represent a distributed load isn't a real thing. It's a mathematical thing that we use. So be sure that you, when you choose how many cuts to make, be sure you're looking at the real loads, like as distributed loads. Don't do it looking at the picture like this one where the weight or distributed loads are represented as point forces, or you'll have extra cuts. And the answers will be wrong. So just think like when where you choose to make your cuts depends on the real loads, actual loads. When you treat a distributed load like a point force, that's for our benefit. Those aren't real things. You know what I mean? So you want to go all the way back to the original thing to figure out where those subfunctions might change. Any other questions?
Yes, sir. And this is we probably covered it and I can't find it in the notes. So internal loads and beams, number 3.
Yeah.
When we go, so I figured out we had 3 cuts on this thing.
Yep.
And I got my M, and I got my T, and I got my my fancy T, my regular T, and V, and that's it? Or do
Yeah.
I need to run them back into, if that's all you're looking for, is
Yeah.
at the end of those cuts, you just
That's it.
fades away. Okay.
Yeah. And then you can do those. It's a good idea to do those checks at the end.
Understand that.
But that's all. Yep.
Well, I finished this one.
See, you were complaining about it, and it was fine.
I had a question, I wasn't complaining on that,
Okay.
and I'm not happy with the answer.
Okay.
Now I have to.
No, yesterday you were complaining about that assignment, if I remember correctly.
I was here till 11.
Oh, really?
Scared the
In that room over there?
Yes, sir. Janitor came in to check the lights, and I scared the heck out of him.
Did you jump out?
No,
Oh.
I was sitting in the back, he didn't see me.
Uh,
Holy Hannah.
Okay, well, let's take a 10-minute break, and when we come back, I'll answer more questions about this stuff if you want, or we'll go on if you're out of questions. This is a question about number 8 in stress tensors loaded like stress element, objects loaded like stress elements. You have this diagonal member connected to let me try that again. No. A semicircular member and there's a 1,000 Newton force acting at that pin. And there are no weights. This is 30 degrees. This diameter is, it says the diameter is 0.6, so this radius is 0.3. The straight member has a length of 0.4. And then it gives cross-sectional stuff. But the first thing you have to do is calculate those external loads. And it's a funny-looking truss, but it's still a truss. Well, if you went to calculate the internal loads in this in this curved member, it would be sort of, things would get a little weird with it. But it's still a two-force member, is what I mean. And so you can still use whatever method you use to find the external loads in trusses. Yes, it's a curved beam. Yep. Did I say straight? It's a curved beam. There are curved beams. Okay, so if we call this one 1 and this one 2, a free body diagram of, I'll do the free body diagrams for both approaches. So first for member 1, you have a force vector down here, I'll call that RA. And up here, you have a force on 1 by 2. And since the pin is lumped in with member 1 here, you also have the 1,000 Newton force. And then a free body diagram of member 2. You have the negative force on 1 by 2. And then down here you have RB. And no 1,000 Newton force because that's applied to the pin, which is member 1. 3 equations here, 3 here. So that's 6 total equations, 2, 4, 6 variables. So you can solve that. If you isolate the pins, so this is 6 equations, 6 variables. You can just isolate the top pin. So there's the pin. You have a 1,000 Newton force on it. You have the tension F1. And now what's the direction of the tension F2 on this pin? That's the thing that's a little unusual with this. But think about the definition of a two-force body. Yep, it's straight down towards the other joint. Because all that matters, so with two-force bodies, you know that those forces are equal and opposite, and you know they're parallel to the line between the two joints. So no matter what this body is doing in between those two joints, you know that has to point to the bottom joint. And then you can just solve it like this. Okay, yep, 2 variables, 2 equations. Any other questions? Homework questions? Yep.
For number 1 through like 3 on the numbers loaded homework.
Yeah.
I didn't get part B when it asked for like what's the stress and stress.
For number 3? For which one?
Yeah, number 3.
Okay, well, you figured out the stress in each one? Okay, so let's say that you got, I don't know, do you happen to remember what those values are?
Which values, sir?
Like in one of these members for that structure. So you got, these are in compression, And that led you to a stress tensor. And what was this? What was the original stress tensor that you got?
That was negative 1.064 into the 6. And then 0 for the
Okay. So once you're here, to calculate the maximum shear stress, you need to get a principal stress tensor and then rotate it 45 degrees, rotate the coordinate system 45 degrees around the middle axis. This one you can skip the step of getting the principal stress tensor because this is already one. There's no shear stresses. So it's already principal. And so now you just have to think about which is the middle axis, which is the axis corresponding to the middle principal stress. The values are 0, 0, and negative 1.06 times 10 to the 6. So either one of these zeros is the middle one. So rotate the coordinate system 45 degrees around y or z. And that'll give you a stress tensor with the maximum shear stress. And, okay, so the resulting stress tensor will have a shear stress with an absolute value of the max minus the min principal stress divided by 2. And so that's 0.532 times 10 to the 6 pascals. But if it asks for the stress tensor, you have to do the rotation thing. If it just asks for the maximum shear stress, then you can just use this formula.
That's always min minus the maximum.
Yep. If you do min minus max, you'll just get a negative answer. It all sort of means the same thing.
Because no matter which direction, it's that magnitude.
It's the magnitude that matters, right?
Rip it apart.
Yep.
So principal stress tensor to use rotation matrix.
The stress tensor with the maximum shear stress, you need to use the rotation matrix to go from the principal stress to that. Yep.
In the solutions, you had that number 1 and number 2 would have the same results, but would it give you different since they have different cross-sectional areas?
They do? Then yes. They'd have different stresses, yes. They would have the same internal loads, but then you divide those internal loads by different areas. Yep, right.
3. Yeah. No, your solution just you forgot that.
Okay. Hey.
Yeah, you said the two bodies equal but opposite,
Mm-hmm.
but they had a different cross section.
Uh-huh.
You must have added that later. The secretary left it all.
Yeah, exactly. It's hard to get good help these days. It's hard to get any free help. Any other questions?
Yes.
Okay.
So I did it's number 6 on numbers loaded according to the rules of stress elements. Just understanding what you're trying to ask us here.
Yeah. That's the one with a big rectangular thing with distributed loads shown
Yes.
in shear around it? Okay. So you have a big thing that has, this length is 0.8 meters. This length is 0.5 meters. And then into the page, there's a thickness of 0.05, is that what it was?
Yes, sir.
And then there are distributed loads acting on all these faces.
And it's just those two faces, correct?
Yep.
I did the same thing I drew this out.
Yep.
And then we could get a stress tensor from that by,
So just take it gives you a total force. What are the values of these total forces?
212,500 newtons on the width,
Okay.
and 340,000 newtons on the heights.
And that also is not a good description. It has to be like this, 212,500.
Yes, sir.
Okay. It has to be like this for this to work out. But if you, so think of this, call this area 1, and this is area 2. Area 1 is equal to 0.5 times 0.05. That's 0.025. Area 2 is 0.8 times 0.05. So that's 0.04 meters squared. And then if you take 212,500 divided by the area that it's acting on, that's equal to 340,000 divided by the area that it's acting on, and that's equal to the shear stress XY. And if you switch the order of these, the 212,500 was on top and the 340 was on the side, it can't be in equilibrium. It would be rotating. What does this mean? So it just means that every point inside that stress element every point inside that body, the stress tensor is 0. What's this value? Can you divide that out for me?
8.5 e to the 6.
So the stress tensor is 0. 8.5 times 10 to the 6, 0. 8.5 times 10 to the 6, 0, 0, 0, 0, 0. And you could compute the eigenvalues and you'd get the principal stresses, and then if you did the 45-degree rotation thing, you'd get some version of this back. This is as big as the shear stresses can be.
Those are just the locations of the sigma xy.
Right. Any other questions?
Why are those two equal?
Why are these two equal?
No, the equation you have.
I mean, yeah, those aren't equal. Why is this equal to this? Well, it is because I made the numbers so that it worked that way. But if they weren't equal, remember, it has to do with the rules of stress tensors. You know, this set of problems is all about members that obey the rules of stress tensors. A stress tensor has to have a shear traction on this side that's equal, a shear traction going this way that's equal to the shear traction going this way. That's one of the rules of the stress tensor. And so if that wasn't the case, this wouldn't fit into that category. And also, if that wasn't the case, it wouldn't be able to be in equilibrium. It would have an angular acceleration.
I mean, on this one, is effectively what I did is I just took it and made the rectangle just like you did, and I said, okay. So it looks like the cube we always draw.
The stress element.
The stress element. So I just said, okay, that's the stress element. That's how I got my faces.
Right. Yep, exactly. That's the idea with all of these. It's just like a misshapen stress element, and you just, and if that happens, you know that the stress at every point inside is the same, and you can get it, you can figure out what it is. Based on the way you go from a stress element to the stress tensor, you do the same thing here.
Yep.
Any other questions? Okay, let's do, so now we're going to, the next thing that we're going to be talking about is stresses due to internal loads and beams. And those internal loads aren't just tension and compression anymore. They can be shear force, bending moment, and internal torsion. And so the structures that we can deal with, you know, so far the structures we've dealt with are all trusses, but now we can deal with other kinds of structures. So I want to do one frame problem, calculate the internal loads in one of the beams of a frame, just to jog your memories and stuff about that. And then we'll get into, on Friday, I guess, we'll get into how you calculate the stresses due to the bending moment, the shear force in beams. So, okay, let's say there's a cable attaching the end of one member to the middle of the other one, and they're connected by a pin, and there's a fixed joint with the ground. And let's say we have a downward force of 1,000 newtons. We're going to neglect the weight. What are the internal loads in the diagonal member? Let's say this is 1 meter long. And this is at the midpoint, which I guess means, and this is 1 meter, half a meter. That means that these are both 45 degrees. Okay. So I'm going to call this member 1 and this member 2. And I'll choose an origin here. And start with a free body diagram of member 1. At the midpoint, we have a force vector on 1 by 2. At the top, we have a downward force of 1,000. And at the left end, we have a horizontal force, T. So I'm going to write out the table. Pancake, artist, row, 4, marzipan. Where this tension force is applied, what are the coordinates?
Or
Did I? Yeah, right. That's right. So negative 0.5, negative 0.5. And then for an about point, we might as well choose the origin because there's a force vector there. We can get it out of the moment equation if we make that the about point. So the row vector for this cable tension is negative 0.5, negative 0.5. The force vector is T0. So the cross product is in the z direction, positive 0.5 T. Then next is the force F12. That's at the about point, so there's not going to be any row vector. The force vector is F12 x and y, and there's no moment. Bless you. And then the 1,000, that is at positive 0.5, positive 0.5. So the row vector is positive 0.5, positive 0.5. The force vector is 0, negative 1,000. And the moment is negative 500. So Newton's second law, add up all these forces, P0 plus F12 x and y plus 0, negative 1,000 zeros. And the moment equation says 0.5 T minus 500 is 0. So our first three equations say T plus F12x is equal to 0. F12y is equal to positive 1,000. And 3 0.5t is equal to 500. This is one of the rare ones where you could actually solve for what we have already. We have 3 equations and 3 variables. Let's not, though, because I like to get as big a matrix as possible. It's more satisfying when you get all the answers at the end, you know? So now, free body diagram of the vertical member. Up here we have negative F12. At the middle we have a cable tension going to the left. And then at the ground, that's a fixed joint. So I'll call that the force vector RA and the couple MA. So first I'll do RA. Let's do this. Let's, for this one, put our origin down here. And then we'll also make that the about point. And the effect then is all we have to do to come up with the row vector is just give the coordinates of the point. Okay, so start out with RA. That is a row vector of 0. Force vector of RAX, RAY. So no moment. Then the couple MA. How does that come into this table? Yep, it's just a pure moment, so just put that in here and forget about all the other stuff. Then we have T. The row vector for that is 0, positive 0.5. Force vector is negative T, 0. And the moment is 0.5 T. And then the last one, the row vector is 0, 1. The force vector is negative F12x, negative F12y. So you get negative F12x. I do mean that. So Newton's second law says RAX, RAY plus negative T, 0, plus negative F12x, negative F12y is equal to zeros. And the moment equation says MA plus 0.5t plus F12x is equal to 0. So our fourth equation says RAX minus t minus F12x is equal to 0. Our fifth equation says RAY minus F12y is 0. And our sixth equation says MA plus 0.5t plus F12x is equal to 0. Okay, so we have 6 equations and 6 variables. So I'll go, I'll call it RAX, RAY, F12X, F12Y, T, MA, and then the constant in the last column. And can someone read me out the coefficients for these? So for equation 1, what do we have?
T
Okay,
plus F12X
okay,
equals 0.
all right,
F12Y equals 1,000.
okay,
0.5T equals 500. RAX
okay, I can see the rest, thanks. So RAX 1, T negative 1, negative F12X, F12X is negative 1, and then 0 constant. For equation 5, RAY we have 1, F12Y we have negative 1, 0 constant. And then equation 6, MA we have 1, T we have 0.5, F12X we have 1, and then 0 constant. And everything I didn't fill in is a 0. So could you guys solve that and let me know when you have answers?
So F12X, F12 I got negative 1,000, 1,000.
Okay.
Function I got 1,000. RA I got 0, 1,000. And MA I got 500.
500? Okay. And we want to calculate the internal loads on the diagonal member. So let's redraw the free body diagram of the diagonal member. That was member 1. We have a horizontal force from the cable of 1,000. We have a force at the midpoint of negative 1,000, positive 1,000. And then a 1,000 Newton force acting down like that. And we want to go from a coordinate system like this to a coordinate system with the x-axis along the beam's axis. So you could do it either direction. You could do it this or rotate it 180 from this. But what's the rotation we need to do to go from this one to this one? Yep, positive or negative? Positive, yep. And about what axis? Yeah. So for that, the rotation matrix is cosine of 45, sine of 45, 0. Negative sine of 45, cosine of 45, 0. 0, 0, 1. Bless you. And so that's .7071, 0.7071, 0, negative 0.7071, positive 0.7071, 0, 0, 0, 1. How does the matrix work? Oh, it's the right-hand rule. So imagine your finger is doing the rotation. Your thumb tells you the direction of the... Yep. Okay, so let's do these force vectors one by one. So the cable, we have this Q matrix. Times what's this represented in components, this 1,000 Newton horizontal force in components. Yep. Hey, your voice is back. Good job. And you get 707.1, negative 707.1, 0. Then we'll do F12. So 0.7071, 0.7071, 0, negative 0.7071, positive 0.7071, 0, 0, 0, 1, times the force vector of negative 1,000, positive 1,000. And so that is 0x positive 1414.2, 0. And then the last one is that external load that was given. So you have the matrix. Times, that was a downward force of 1,000, so 0, negative 1,000, 0. And you get negative 707.1, negative 707.1, 0. So now you can redraw this problem like this. Positive 707.1, negative 707.1. In the middle, you just have an upward force of 1,000. No, 1414. And then on the right side, you have negative 707.1, negative 707.1, 0. And now it's a simple internal loads problem because there's no distributed loads. What's n for this? N is 3, 2 cuts. Yep. Any questions about that one? So I guess on Friday I'll do that internal loads to finish this one.